guys. So this is another example. So we will study these model example, maybe 4 model examples, and based on these types of examples, we will solve problems in the future, right? So this is an example for a particle of mass m attached to an elastic string. So this particle is attached to a fixed point on a wall, let's say A, by an elastic string. So elastic string is the connection between the wall and the mass. And when we have an elastic string, it should have a natural length. So natural length is taken as L, and there should be an elastic modulus. Well, let's call it mg for the moment. Right. So the first part is show its simple harmonic within OB and find the center. So O is the equilibrium point. Now we have to show that these particles move under simple harmonic motion within this region O and B. Why? Since this is an elastic string, if it displaces the particles by a small amount, it will be under tension in this region O to B. If it is here, it will be under tension. But if it moves beyond O towards A, within this region A and O, it does not have any tension, right? The force vanishes. So it will not behave in this part, in this region from A to O. So this particle will be an example for a particle that is in partly simple harmonic motion, right? So whenever you are asked to show that it is simple harmonic, then you can have to show a general position of the particle under stress. So this is mg, this would be r, and there will be a tension. Okay, now put F equal ma to any side. Suppose the particle is moving in this direction now. Then the tension is to the opposite direction, minus T. That this is the only force, M x double dot. So how do you find tension? So tension is given as lambda x tension divided by its natural length. Now lambda is mg, so minus mg. This is the extension from O x divided by natural length m x double dot. So m goes off, and you have d over L x equal x double dot. Now this is the characteristic equation of simple harmonic motion. You know, this is equivalent to its characteristic motion, right? Where omega squared equals d over L, right? So since it looks like the characteristic equation, then we can say that this particle behaves simply harmonically, right? And find the center. To find the center, how do you define the center? You define the center by this. At the center, the acceleration is 0. That's how we define the center of a simple harmonic motion. The acceleration must be 0. So acceleration is 0 means x has to be 0, because omega squared is not 0, so x has to be 0. This implies x is equal to 0. Now what is the center? So x equals 0 means this point O is the center. This is the center. Right, so this is the first part, part A, and let's look at the part B next.